Hello and welcome back to Fourier Transform, the video series where we talk a lot about Fourier analysis, in particular the continuous Fourier transform. And indeed, in today's part 24, we will finally give the definition for the Fourier transform as an integral transformation. However, before we do that, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady member you get a lot of rewards, like PDF versions, quizzes and books. Just click the link in the description to download them. And then I would say we can immediately start with the definition of the Fourier transform. In the last video we have already discussed how this definition should look like when we come from the Fourier series. And now we will extend this to all integrable functions defined on Rn. More precisely, we work in L1, which is a space of equivalence classes of Lebesgue integrable functions on Rn. The most important part for us is that this is a vector space with a norm. And in that sense, the Fourier transform is a linear map. And I will denote this abstract map by a curved f. And as already mentioned, the input space is given by the Lebesgue integrable functions. However, the best choice for the output space we don't know yet, but we can choose it as large as we can with the function space of functions defined on Rn. So the Fourier transform will definitely map into this space, but we will show in this video already that we can make it much smaller. In fact, the image of a function f under the Fourier transform, denoted by f hat, is always a continuous function on Rn. So you can already remember that, but before we can prove it, we should first write down the definition of f hat. And in the following I will always use the variable name p for the functions on the right hand side. On the other hand, the functions on the left hand side will get the variable name x. Now at this point you should already know that the Fourier transform is an integral transformation. And for the reasons we have discussed in the last video, we have a constant in front of this integral. It's 1 over the square root of 2 pi to the power n. So the dimension of our space Rn also goes into the constant. And then the crucial part inside the integral for the Fourier transform is the exponential function where p and x go in. However, p and x are vectors in Rn, and what we actually have here is the standard inner product of p and x. And to denote the standard inner product, I just use this big dot and not the pointed brackets as usual. Simply because we also have to deal with other inner products, for example, inner products of functions. Therefore, I want to use a simple notation for the standard inner product in Rn. And usually here we just have it inside the exponential function anyway. Okay, so there we have it. This is the whole integral transformation we call the Fourier transform. F just goes inside the integral and the integration is a linear map, so the whole thing is definitely also a linear map. We don't have any problems here, which means the integral exists for any point p, simply because f is an integrable function. And here you can remember that the Fourier transform is an example of an integral transformation where the integral kernel is given by this exponential function. And you might also know other integral transforms like the Laplace transform or the Hilbert transform. So they are all related in the definition, but they have different properties. Indeed, you might see that the properties of the Fourier transform can be really helpful for solving partial differential equations. However, here you should recall everything we have done for the Fourier series, which showed that considering L2 functions might be more helpful for understanding what the Fourier transformation actually does. Indeed, the square integrable functions have a nice inner product, also defined by an integral. However, in the continuous case here, this is all not so simple because L2 is not just embedded in L1. So in contrast to the Fourier series, this is just not a special case of the L1 case. And moreover, it also does not work the other way around, so we really have two different cases here. So please keep that in mind. When you see the Fourier transform somewhere, you also have to check the domain of definition given there. And here we will first start with the case that the domain of definition is given by L1. And for that, as already mentioned, the first result is that the output is always a continuous function. More precisely, we also get that f hat is a bounded function. And the common notation for that is a capital C with index lowercase b. So this is the vector space of functions from Rn to C which are continuous and bounded. Moreover, also this space has a nice norm given by the supremum norm. Hence, this is exactly what we can check now, namely that the supremum norm of f hat is finite. Hence, we can just use the definition of the supremum norm in Rn. So we take the absolute value or the modulus of f hat at any point p in Rn. So this is already the whole thing, so not complicated at all. So we actually just have the absolute value of the whole integral. And there you know we have the triangle inequality for pulling the absolute value inside the integral. So we immediately get our estimate, which should be good enough to show that we have a finite supremum norm. Indeed, we already know that the modulus of this exponential function is equal to 1 no matter what x or p is. Therefore, the supremum over p does not change anything and we can just omit it. So we just have to integrate f absolutely, and we already know this is a finite number because f comes from L1. In fact, this is exactly the L1 norm of f. So by assumption, this is finite for any input of the Fourier transform. In other words, now we have already shown that the output f hat is a bounded function. So it only remains to show that we also have a continuous function there. And you know we can formulate this with sequences, so we take a sequence pk in the input space, and we assume that this sequence converges to a given point k. And then continuity at this point p would imply that we also have convergence in the output space. Or to say it more precisely, the images f hat of pk also converge to the image f hat of p. And now if this property holds for any point p in the domain and any chosen sequence pk that converges to p, then we have continuity everywhere. So this is how we usually define continuity, and please note here on the left we have convergence in Rn and on the right we have the convergence in C. Moreover, there on the right we have to deal with integrals, so the integration theory and measure theory can help us there. More concretely, we can apply Lebesgue's dominated convergence theorem again. And in order to do this, you might already know, we need a sequence of functions, so let's call them gk. And this is quite a natural definition, we just have to take everything we have in the integral except f. So it's the constant and the exponential function given at the point pk. And obviously for any point x, this value converges. Obviously this converges to the same function, but it has p instead of pk as an input. Therefore it makes sense to call this function just g. So the naming here is useful because from the beginning we fix a sequence pk and a point p. And now you see we have this convergence here for every point x in Rn. So this pointwise convergence is one requirement we have for Lebesgue's dominated convergence theorem. And the other part is, as the name suggests, that inside the integral this function is dominated by an integrable function. And this one is quite clear because exactly this calculation we have already done before. So this is the function we want to integrate for any k, and it is definitely smaller than the absolute value of f, because this constant is smaller than 1 and the modulus of the exponential function is equal to 1. And now the only thing we need is that almost everywhere we have this inequality and that f is integrable. So this is our dominating function and the theorem is applicable. And it simply allows us to push the limit into our integral. In other words, we can simply use it to calculate the image f hat of pk. In our notation, this is simply given as the integral of gk of x times f of x. And now if we perform the limit k to infinity for the integrals, we can just look at the pointwise limit inside. Which simply means we get the function g of x times f of x, which is exactly f hat of p. Hence the continuity of f hat is shown for every point p, and our first proof is done. So now you know, your input for the Fourier transform can be really not continuous at all, but the result is always a continuous function. And in order to see that, let's look at an explicit example. However, this is something for the next video, so I really hope I meet you there again. Have a nice day and bye bye.